This is Project 5, or Group 6. So, first, we're going to be talking about insulators. So, insulators are materials that don't easily transfer electricity. So, these are something that are going to keep those electrons in and not share them or transfer them out. So, how you can think of this is when you wear a coat, that's going to be keeping the heat in and keeping the cold out. So that's an insulator. Another form of an insulator would be like an animal pellet. Animal pellet is doing the same thing for the animals, where it's keeping that heat in and not allowing the cold in. So that's how an insulator works, is just preventing that flow of whether it be electrons or heat or whatever. So conductors are the opposite of an insulator. They're going to easily allow the flow of electricity. So first example I have here is a frying pan. So a frying pan, when you heat it up, it's going to get very hot. When you put your food in it, it's going to transfer that heat into your food in order to cook it. So that's the same thing that this wire is doing, but with electrons. It's going to be allowing the flow or the movement of electrons through that wire. And the last kind of material we have is semiconductors. So semiconductors are not usually allowing the flow of electricity, but they will if there's an external force or excitement. So in the regular state, they're kind of like this calm river with no external forces, there's no current. So if you were to throw like a leaf or a piece of wood onto this calm river, it's not going to flow anywhere. Where on the other hand, there's this river that's flowing very fast, whether it be current or wind that's moving it. There's an external force pushing the water. So if you were to throw a leaf or wood into that, it's going to push it down the river. And that's demonstrating how the electrons would flow through a semiconductor. So the three types of primary bonds that we have are going to be ionic, covalent, and metallic. So the first type is ionic, and this is going to be where the electrons are transferred from one another. So if I can have Cole step here for a second. So if I'm an atom, he's an atom, this is an electron. Ionic is going to transfer that electron there, and now we're bonded together. The second type is covalent. So the electrons are going to be shared. So again, I'm an atom, he's an atom, this is an electron, and we're going to share this, and we are bonded together. The last kind is metallic. And that's where this electron is just kind of floating freely about, and it just kind of goes back and forth to other electrons or to other atoms as it moves through this kind of sea of electrons. So those are the three primary bonds and how they work. If we move on to secondary bonds, the two main ones we have are van der Waals reactions and hydrogen bonds. So van der Waals are kind of like those sticky hands you get like from the arcade or whatever. So it's going to stick for a short period of time, and then it's going to remove itself. So that's what a van der Waal is. It's a short temporary bond between molecules. A hydrogen bond is a special bond that only occurs between hydrogen and then oxygen, nitrogen, or fluorine. And they're stronger than van der Waal, but weaker than primary bonds. So that's kind of like your prom date. So it's a little bit stronger than like just an acquaintance, but it's not quite as strong as if you were married or dating. So it's kind of it's a strong bond, but it's not the strongest it could possibly be. Finally, we're going to be talking about energy bands. So atoms have different levels of electrons. When many atoms form together, those electron levels will form into bands. The two bands we're concerned with right now are the valence bands and the conduction bands. Valence band is the electrons that are bounded to the atom. And then the conduction band is electrons that can move freely between different atoms, and they can conduct electricity easily. The band gap is the distance between those bands in the electron, or excuse me, in the atom. And if the gap between these bands is small enough, the electrons can move from band to band when they get an external energy like heat or something else. One more thing, resistance. So in our lab, we were looking at different resistors and how they worked. So different materials and wires with different lengths or thicknesses will have different resistances. The longer the wire, it'll have more resistance. The thicker the wire, it'll have less resistance. In our case, we were just using regular resistors. They weren't changing length or thickness, but the resistivity of them was changing, and we saw that it was not allowing as much electricity to pass through. So what we used to look at the length was a potentiometer. So the farther apart the connections were on that potentiometer, the greater the resistance. It's just kind of a big resistor that allows you to put different connection points on it. And then looking at the thickness, we have like a three-way highway and then kind of like a backcountry highway. And that's showing how a thicker material is going to allow for more electrons to flow, and then a thinner material will have a little bit more congestion and not as much flow with those electrons.
So next we're going to talk about conduction extrons and then holes for them. So it's a good way to think of electricity and the negative electrons that are found within an atom, like cars in a parking lot. So you see each of these cars, they're filling up these spaces within this parking lot. And then if a car leaves its space, let's say, this now becomes an open parking spot. So it's good to think of this of like how electrons, if they leave their space in the atom within the structure, this opens up a hole within the atom. And then these holes and then these parking spots, they move around freely within this parking lot. So holes can be considered as positively charged, and then the cars and aka the electrons, they can be viewed as negatively. So it could be good to visualize these as both moving around in this parking lot within the atom. And then this takes me to mobility. So mobility is pretty much just how easily these electrons and these holes move throughout the body. So it could be nice to see in a analogy where if an atom has a high level of mobility, it's like driving on a highway with multiple lanes. But if you have low mobility, it's going to be harder to drive around, harder to move, and that's going to be like the equivalent of driving on a dirt path. And so that takes us to the intrinsic versus extrinsic semiconductors. So an intrinsic is a pure material where electrons and holes can be created naturally. So when you add heat, the amount of electrons are going to be excited, and the number of holes that get excited is going to be linear, so they're going to be naturally created equally. So some examples of this are going to be silicon and germanium. And then comparing that to an extrinsic, it's going to be a doped material. So that's where we take impurities and we put it into the atom. So for example, if we add phosphorus to a silicon, it'll give us extra electrons. But if we add boron, this will create holes. And it's important to change the behaviors of this, as this will allow us to, since we have more holes, it's going to increase the conductivity of this material, which is essential in some processes. So an example of this between the two is going to be silicon and STP. Since that has a moderate level of mobility, it's going to allow electrons to move a little bit faster than the holes are. But if you compare that to germanium at standard temperature, it's going to have a higher mobility than silicon is. So this is going to let the electrons and holes move more freely compared to those found with silicon. So if these electrons and holes are moving more freely, that's just going to mean that the amount of holes that are going to be created are going to go up, and this will allow us to have the conductivity increase as well. And so this compares us to the next thing, so where gallium phosphide compared to gallium arsenide. So why is one green and then why is one infrared? So this has to do with the band gap found within semiconductors. And this is pretty much just how much energy is released when they move around. And that can be compared to like a diving board. If you have a large band gap, that's going to make it so you're jumping and you're creating more energy, and the bigger splash you have can be compared to the bigger energy you have. So in the example of gallium phosphide, since it has a larger band gap, the level of energy that is released when it lands correlates to a level of energy that's typically higher. And each energy has its own correlating range for what light it could be. So for this large band gap for gallium phosphide, it's going to correlate to a green light being emitted. And then for gallium arsenide, since it has a smaller band gap and the energy that it releases isn't as high, it's going to fall within the range of an infrared light, which is not seen by the human eye.
So now we're going to talk about different silicon conductors. So as we learned in class, silicon is an element that has the ability to form 4 covalent bonds with its 4 valence electrons. And these covalent bonds are formed with the crystal structure around this atom. And in intrinsic silicon conductor, it's going to be pure silicon all the way through. So there's going to be silicon atoms all linked together with these covalent bonds. There's no impurities. There's none of that. Everything is the same. The amount of holes is equal to the amount of electrons. So if we look in our material science textbook, we can see that the mobilities are 0.45 meters squared over volt seconds, and or that's for the electron, and the mobility for the holes is 0.050 meters squared per volt seconds. So what the mobilities are, it's the ability for the holes and the electrons to scatter throughout. So there's a little bit of random chaos happening throughout this entire thing. So in a wire, all the electrons aren't just going in one direction. They're really bouncing all throughout. So the same thing is happening here in this resistor. As the electrons are going through, they're bouncing all around, and there's no true path. Well, they're going in one direction, but they're not all going the same direction at the same time. And the conductivity is just pretty much how freely these electrons are able to move. And so the conductivity of the intrinsic silicon at 300 degrees K, which is room temperature, I forgot to mention that, is 3.4 times 10 to the negative fourth, 1 over ohm meters. So with these values, we can reverse engineer our conductivity equation to figure out the concentration of these electrons and holes. Now, since this is an intrinsic semiconductor, the holes and the electrons are both going to be the same. The concentration for both will be the same at every temperature. So what we can do is we can reverse engineer the conductivity equation to give us Ni, which is the concentration of both the holes and the electrons, which it can really be either or. It's not them together, it's them separately, it's just the same number. And so we also use E, which is the absolute value of the charge on an electron, and that is 1.6 times 10 to the negative 19th coulombs. So when we put this into our new equation here, we find that our concentration is 1.09 times 10 to the 16th per meters cubed. Yes. So with this, we can calculate the resistivity of an intrinsic semiconductor. So the resistivity is simply just the inverse of the conductivity. So simply we could just put 1 over the conductivity, and that'll give us the resistivity. Next, we're actually going to find the resistivity of, we're going to find the resistance of a 1 millimeter square by 1 centimeter long resistor made of the pure silicon. So in order to do that, like Nick said, we have our resistance is equal to rho, which is our resistivity, times our length, all divided by the cross-sectional area. I converted these up to meters, and so when you put all this through, the meters will all cancel, and we get 2.94 times 10 to the 7th ohms. So when we increase the temperature for this intrinsic silicon semiconductor, we'll see that the concentrations will increase as the temperature increases. This means that as thermal energy is added, these electrons are going to get excited. They're going to want to bump up to higher energy levels. And so when they bump up to the higher energy levels, they're creating holes at the lower energy levels. And so as the temperature increases, obviously more of those electrons are going to bump up and more of the holes are going to be formed on the lower levels. So for an extrinsic silicon conductor, this is where impurities are added. So you would add impurities to change the resistivity and change the way that they act. So So there's two main types. There's an N-type and a P-type. An N-type is where you have an element that is added to the silicon semiconductor that is a group higher. And with it being a group higher, it has one extra electron. And that one extra electron is going to bounce around. It'll orbit that impure atom. And when an electric field is added, obviously it'll start moving back and forth with the others. But this electron is just going to be bouncing around. It's not going to be connected to anything in a covalent bond. It's too weak. It's just going to be bouncing around. And with the P-type extrinsic semiconductor, we add an atom that has one less valence electron. So that is creating a hole. And that hole can be filled by another electron from another silicon atom, but that also creates another hole. So there's gonna be these extra holes that are gonna be in. So the N-type adds another electron, the P-type adds another hole. So we're asked to figure out So we're told that our silicon semiconductor from before is now going to be doped with 2 times 10 to the 19th per centimeter cubed boron atoms. Now, boron is a group lower than silicon, so that means we're going to create a P-type semiconductor. So there's going to be more holes than there are going to be atoms. So, yeah, the concentration of the concentration of the electrons is going to stay the same, and the holes will be increased. So, like I said, the concentration of the electrons is going to stay the same, but now the new concentration of holes is going to be this, is P is equal to 2 times 10 to the 19th centimeters cubed, or when we convert it to meters, it's 2 times 10 to the 25th meters per meters cubed. And so now we can solve for the electroconductivity, but we're going to use a different equation. This is the equation for a P-type semiconductor. So we have P times the electron charge, the absolute value of the electron charge times the mobility of the holes. So when we do all this, we get 1.6 times 10 to the 5th per ohm meters. Now we can use this again. We take the inverse, we can figure out the resistivity, and then we can figure out the resistance of the same resistor now doped with the boron atoms. And that comes out to 0.0625 ohms. And so when the temperature increases, obviously the atoms are going to get excited, and there's more holes than, not atoms. The electrons are going to get excited, and there's more holes than the electrons. So this is going to make the material more conductive as it heats up, and obviously the resistivity will decrease as that conductivity increases.
That was a much longer presentation.